I'm very proud to welcome you to our webinar of our Nexperia ESD seminar series. Today we are talking about ESD protection for automotive interfaces. Before we start, let me share with you some background. Around 2 years ago, my team of engineers created our first ESD application handbook with focus on protection concepts, testing, and simulation for modern interfaces. We are covering in this edition the fundamentals and a broad range of different applications like communication, computing, automotive, etc., including insights of a lot of interfaces like USB, HDMI, MIPI, and focus for today is of course the automotive IVN interfaces. I'm sure some of you already received the book. It is designed for you from engineers to engineers. The ESD handbook is part of a series of technical handbooks. We have the power MOSFET application handbook, and we are working on a new one with focus on logic products and the application, where we also are planning seminars to explain to you more. Coming back to our seminar today with focus on automotive. Ever increasing connectivity, keyword like autonomous driving, for example, leads to an increase in the amount of data which needs to be transferred into the car. High ESD robustness is key to ensure the reliable and high performance demanded by modern automotive applications. The challenge hardware designers face is that the data rate increase and the ESD robustness decreases. So to address the dynamic and demanding challenges faced of today's automotive industry, we decided to publish a special edition of our ESD application handbook. We call it Nexperia's ESD application handbook Automotive Edition. The PDF is published on nexperia.com and a hard copy version will be available soon. Please contact our sales teams. And of course, today's seminar is covering a lot of automotive topics. Let me introduce to you the presenters. Andreas Hardock is a member of the application marketing team. He studied at the University of Würzburg and later finished his doctoral degree at the Technical University of Hamburg in 2015. He is here also that he has a lot of background in the industry, working for BHTC and Continental, and joined Nexperia mid of 2020. Together with Andreas, Lukas is the second presenter, and Lukas is a product manager for protection and filtering with focus on automotive, working for Nexperia since 2018. He has a bachelor degree from the German Nord Academy and is our expert for in-vehicle networks such as CAN-FD, infotainment, and Open Alliance Ethernet. As mentioned, at the end, we will have a Q&A session, so feel free to type in your questions. We will collect all questions and cite aloud later, early next week, a document with all topics. Dear Lukas, let's now move on to the real important technical stuff.
Thank you, Olaf. And again, welcome to the second edition of the seminar. But before we continue about discussing automotive applications, let's have a quick recap of what we discussed on Tuesday. So on our first session, we discussed the fundamentals of ESD protection. So we discussed the why do we talk about ESD protection, and we focus a lot on the difference between device and system level perspective. And then moved on and discussed what are the selection criteria we have to consider when choosing a good ESD protection. We presented to you the key parameters or key factors, and we also showed how we can measure and characterize them. So in today's session, we will apply our latest learnings from Tuesday to the most common automotive interfaces. We will start with the low speed buses, and then move on to Automotive Ethernet, SerDes, infotainment buses. And then we prepared also a little extra for you because of the last session we got some questions regarding package aspects. So we will add this to the presentation, and then, as Olaf said, we will have our Q&A session at the end. It was Henry Ford who once said, you can have any car you want if it's black. This statement is not sufficient anymore. So the customer needs and expectations to cars evolved, and we have those mega trends happening in the car of increased connectivity, electrification, in order to achieve also autonomous driving. One key there is, of course, data transmission. And with all those new technologies and assistance services we have in the car, the data payload in the car that needs to be transmitted is increasing rapidly. And therefore, we need new protocols, let's say new streets, how we transfer this data. And we now come from this hierarchical network where we have an end-to-end connection to the, let's say, IP-based car with Automotive Ethernet, where we can realize all the software demands we see in the car happening there. So we will start with the low-speed device protocols, as said, starting with 20 kilobits per second, and now Andreas will talk about the LIN bus.
Okay, thank you, Lucas. So as you have seen, Lucas showed you a lot of networks for a lot of car networks, but there is this LIN, which we will still see for the next time for sure. Yeah, it's low speed bus. It's only 20 kilobits per second, but it's simple, it's easy to use, and it's really cheap. And as an experience looking on this from the ESD protection point of view, there are several requirements on the ESD protection. So basically, there are some car OEMs which define or which have some approval list, and in this list are all the devices and also the protection devices listed, and you can choose ESD protection device from this list. But there are also other car OEMs which make a general requirements on the LIN network itself, and based on these requirements, you choose the ESD protection for your specific design. But nevertheless, there are some common requirements on the LIN, and so looking from the signal integrity point of view, this due to the fact that this is a low speed bus, so also the most important parameter, the parasitic capacitance, is not really tough here. So it's for LIN slave, it's roughly 220 picofarad in total for the LIN bus in the car. And usually for the ESD protection itself, there is roughly 30 to 100 picofarad in maximum left as a margin for the ESD protection. So due to the fact that LIN is operating in a kind of very rough environment and it's working with the battery voltage, there are some other requirements, general requirements who need to be considered, and this is the short battery and jump start requirements. So there is this ISO norm which says the ESD protection device is not allowed to operate or to be activated below 26 volts. And there are also some other requirements. There's internal requirements which says not below 28 volt. As we said in our previous session on Tuesday, so the clamping voltage should be as low as possible. But here you see that there are also some other requirements you need to consider here, especially this short battery and jump start and this ISO norms. So you cannot be below to choose the clamping voltage very low, below 26 volts. So on the right side, you see the basic schematic of LIN, and this is the LIN transceiver itself, and we have the connector on the right side. And what we learned from the last time, and we will see it during the whole presentation today. So our recommendation, this is a strong recommendation, is that you should put your ESD protection device here as close to the connector as possible to perform or to protect your network, your LIN transceiver the best. So more specific requirements on the ESD protection itself. There are no really tough requirements or not general requirements on the ESD protection, but there are some compliance tests described in this ISO norm, and these are, or those are done for the transceiver and ESD protection combination. So you need to do these tests or the CARO for compliance. These tests are done for the combination of LIN transceiver and the ESD protection, and basically there are 4 clusters of tests. And the first one is ESD, and this is no problem at all. RF emission is also not usually related to the ESD protection. The immunity to transients, which simulate some pulses on your battery lines, is also not a problem for the ESD protection, but there's this RF immunity, which might be some problems here and there. In 99%, there is no problem at all, but sometimes there is a problem with this RF immunity test with the DPI, so this direct pulse injection. This is the test where RF noise is applied to your system, and the key here is that the system is not allowed to absorb too much power, and therefore these limits are shown here in yellow. So this is a frequency sweep here up to 1000 megahertz, so up to 1 gigahertz, and the key is here not to be below these limits, so not to absorb too much energy in your LIN system. Okay, as we said, it's usually not a problem, and from time to time, if there is a problem, the key solution is here to change your ESD protection in order to have a higher clamping or trigger voltage. So because there are some transients with the high voltage transients within this test, and if you increase your triggering voltage, you avoid clamping of your device. Okay, we'll move on to CAN, and there, as you know, within the CAN there is a lot of variants available. So starting from low-speed CAN to high-speed CAN, CAN FD is now very popular, and also CAN XL is in discussion and will come probably in the next years. So from the perspective of the ESD protection, there are similar approaches. So there are car OEMs which have this approval list with specific part numbers which are allowed to use, and others may only these general requirements on the network, and you choose the device, the ESD protection device, by yourself. But there's also some common requirements from the signal integrity point of view. There we need to look on the parasitic capacitance, and due to the fact that we have higher bandwidth here, so CAN high speed is up to 500 kilobits per second, CAN FD is going up to 5 Mbits per second. So there is for classic CAN 17 to 30 picofarad of maximum capacitance, and for CAN FD it's for some car OEMs it's the same requirement, and others say, okay, the parasitic capacitance should be below 10 picofarads here. And we have here for CAN, it's usually a differential signal here. So we have 2 lines here, CAN high and CAN low. We need to protect both of them, and usually there are 2 ESD protection devices in one package. And here, to keep the symmetry of the lines, also the capacitance matching means the difference between both ESD diodes here needs to be taken into account. So there's usually the difference between the capacitance should be below 1% here. And here again, also other requirements as short battery and jump start needs to be considered also for CAN. For the testing itself, for the ESD protection itself, there are kind of similar tests required, at least on the first look, and defined this in these IEC norm here. And you see the tests are kind of similar to LIN, but if you look deeper, there are very significant differences. But again, so we want to go into the detail of each of this, but the first two, ESD, RF emission, and also the immunity to transients, are usually really not a problem for the ESD protection device. And this RF immunity, again, can be here and there a problem. And but again, if there is some issue, you need to choose a device with a higher triggering voltage. But one hint here to this DPI, in different to the DPI LIN, tests for LIN, there is also another case here taken into account. Due to this differential signaling, there is a possibility to have some unbalanced lines. So there is an unbalancing applied, and therefore, for sure, there is a possibility to have higher RF noise with higher energy, and therefore also these tests, this unbalanced test, needs to be taken into account here. But this is, as we said, usually not a problem. So in addition, and also to recap the first session on Tuesday, we want to show you this TLP graph, this IV curve you might remember. So here we plotted our ISD protection device here, which is triggering at around 37 volts. So this is ISD protection for CAN. And here it's going up, and here the point where the dynamic resistance counts. But we also plotted two ESD protections of two different PHYs. So the internal ESD protection of these PHYs, and you might ask yourself, so if I combine the ESD protection device with one of this PHYs, what would be the best match, or what match would even work here? And the answer here is that if you're having this PHY here, the red line, so the internal ESD protection of this PHY is clamping very low, and so taking also the entire energy of the pulse. And usually this PHYs, such PHYs are not built to be able to take all the energy, and will be damaged here for sure. But this combination is much better. The ESD protection, the external ESD protection here, is triggering first, and also have the chance to take all the ESD energy. And due to the fact that this built also to be able to take all this energy, this combination will survive the ESD test for sure. So then we move on to the Ethernet section.
Thanks, Andreas. So as I introduced in the beginning, we need Ethernet in the car in order to allow or to handle this increased data payload, and there the open alliance formed with all major car OEMs and tier ones and other suppliers in the industry to discuss the standardization of Ethernet usage in the car. And there's one special factor. In the classic Ethernet approach, we see that the ESD protection is placed directly in front of the PHY and behind the common mode termination, and that is okay, but it's not the best class, because we have again this dual sourcing situation, and we have to match the internal protection of the PHY with the discrete ESD protection, as Andreas just showed. Whereas in the open alliance, this ESD protection is moved right at the connector, in front of the common mode termination and in front of the PHY. And here the dual sourcing situation is uncritical, because we now decouple the internal protection behavior of the phi from the discrete ESD protection. But with this new placement of the ESD protection, we also have new electrical requirements. But first, let's show some proof of concept. So here you see a test PCB where we have here the connector, and at the top there's the phi. In this case, we have no ESD protection on the left-hand side. In the middle, we have ESD protection right at the connector. And here we have the ESD protection in front of the phi. And this here is now in blue color scale because we use this EMI scanner where we measure the current density with an H-field probe. And if we then shoot this ESD pulse on our test circuit, then we see in the first case without ESD protection, there's a lot current running through the traces into the phi. So again, red color means high current density, meaning high electrical stress. And here we see that a lot of current goes into the phi and can cause here this micro level damage in the gate oxide. On the right hand side, we see the classic approach, and here we see less electrical stress at the phi, but still a lot of current goes through the traces here. But if we take a look on the open lines set up in the middle, we see here that the vast majority of the energy is guided to ground right with the ESD protection behind the connector, and we see a little electrical stress going through the contamination and the phi. But as I said, if we have this concept, we have new electrical requirements, and there are also some special tests that must be considered, and Andreas will explain them a little further for you.
So thank you, Lucas, for showing us this nice picture. Here we could clearly see what is the benefit of putting the ESD protection right in front of the connector, and this is providing by far the best ESD system level robustness. Okay, we move on to the open alliance ESD protection, and here this is the first time that we have really a specification for the ESD protection device, and there are some general requirements and also some additional tests we want to talk about today. And the general requirements are also very specific here for the Ethernet. And the first one is that the ESD protection device needs to have a trigger voltage above 100 volts. So this is very untypical because it's a kind of very high voltage, and this is basically due to this immunity to this DPI tests. Also the DC voltage, DC working voltage should be at least 24 volts, and this device, so this is basically due to this shorter battery requirement. The device should be a bidirectional device, and it should survive 15 kV IC pulse. So 15 kV, you might say, okay, this is well, not really hard. It's yeah, normal, but the tricky part is that the device should survive 1,000 discharges here, and this is really hard also for dedicated ESD protection device. Okay, then we will move to some additional tests, which are also some kind of special for this Ethernet, and which we do not have for CAN or LIN or something. And we want to go to all of them, to all four. The first two will be somehow related to the signal integrity, because due to the higher bandwidth and higher data rates here at Ethernet, not only ESD should be considered at itself, yeah, this is for sure, but also the signal integrity is considered here very strongly, and we want to address this here. Okay, the first test is the S parameter measurement test, and here you might remember for CAN and LIN, we talked about the parasitic capacitance as a parameter or as an indication how good the ESD protection will be from the signal integrity point of view. Here we do, it's a much more deeper analysis. It's taking care of the S parameters. And here we look at the S11 and S21 parameters. For those of you who are not familiar with RF engineering and scattering parameters, specifically, these one are giving you an indication how much of the signal which you put in your system will be transmitted or reflected. So the reflection is shown here with this S11 parameter, also called return loss. And here the reflection should be as small as possible. And there are also some limits here in yellow, and you need to be below the limit. S21 is saying something about how much of the signal is transmitted through your system. So here also the impact of the ESD protection device should be as small as possible. So in ideal case, the entire signal should be transmitted, and the ESD protection have no impact at all. But for sure, in reality, there are some limits here, and you need to be here above the limits. So, and due to the case, this is a logarithmic scale here, and so 0 is the maximum. So in addition, and due to the fact that we have a differential signaling, we want also to have only differential mode. So the common mode is not wanted here, and therefore this additional mixed mode parameter test is done. And this gives you an idea how much of the differential mode is converted into the common mode, and therefore also the targets are kind of very tough. So this limits, this yellow line, very low, and then you need to be here below the limit. Okay, the second test is the damage from ESD, but it's again related to the signal integrity. And the idea of this test is very interesting and also kind of new. What you do here is you measure the scattering parameters, again, reflection, transmission, and also the mixed mode parameters. So you measure it on your device, then you apply ESD, 8 kV, 20 discharges, 10 plus and 10 minus, and afterwards you measure the scattering parameters again. And the target here is also very tough. You are not allowed to deviate at all. So the curves should be on top of each other, and what you also see here, and as you might ask yourself why it's this a little different, especially here for the mixed mode part, different to the pictures we showed you previously on the previous slide. This is is coming from different PCBs, so test PCBs which were used here. So the next post is the ESD discharge current measurements, and this is also very interesting because you might remember this topology, this Ethernet topology, where the Ethernet network here containing of the PHY itself, so the IC, the common mode termination, decaps, common mode chokes, sorry, decaps, common mode termination, and also the ESD protection here, which is placed close to the connector, as in Open Alliance, the recommendation of the Open Alliance, and we shoot with the gun on the differential on the lines. So, and what we do here is we replace the PHY, we replace it with a resistor network just to be able to measure the currents which might flow into your PHY, and to measure this current, and then to judge if the currents are too high or too low. And therefore, you see here the plots. There, the currents, the real currents are shown over time, and also some limits are shown here, which you're not allowed to exceed. And you see there, there are basically two limits, and taken from the JEDEC norm of the human body model for 2 kV PHYs and 4 kV PHYs And here is the point that you need to be below the limits for sure, but if you're kind of touching the limits, it doesn't mean that your device will be destroyed. It's only an indication here. Okay, and then the last one, and this is the unwanted clamping part. And the unwanted clamping is the similar to this DPI test we talk about in CAN and LIN. So here is an RF noise applied to your system, and the target is that your system is not allowed to adopt too much energy. So there is this limit of about 20 dBm, and what you do is you make this frequency sweep, and you need to stay below this limit here. And this is the test result, and this is also, as we said, is referred to these trigger voltage of 100 volts, because during this test there are also some amplitude can occur which are kind of very high, and the requirements on the ESD protection devices that is not allowed to clamp too early here, and that's why these tests and these trigger voltage requirements of 100 volts. Okay, this was the Ethernet part, and you might ask yourself how much, or whether the results are done for 100 Mbit T1. There are also 1 gig available for automotive already. The requirements on the ESD protection are similar, but with a little tougher limits here. So this is one point, and there's also in discussion this 10 Mbit Ethernet, but right now there's no final specification for that, but probably it will match the CAN FD or CAN XL requirements somehow. So there is a overlap, will be probably, but it's on discussion right now. So what we, as a side remark and an example, and also to recap the last session from Tuesday, I want to show you an example of how important the clamping voltage is for your system robustness. And therefore, we want to show you the performance of a silicon part with this TLP curve, and with another part here with comparable higher clamping voltage. And what we did here, when we used this Ethernet network, and we placed both devices, or first one and then the other devices here close to the connector and shot with the ESD gun. And what we did here is we measured the currents which into the phi, and for this ESD pulse of 6 kilovolts, we measure this currents, and you see here a clearly difference. So when you look at the first time, or on the first a few nanoseconds, there's probably no difference at all. But here further in time, you see that the device with higher clamping voltage here, here we have really also really high current, which is flowing into the phi, and is also hitting here or violating the limits. And if we look at the snapback device, so the current is very low, and we also passing these limits. Okay, that was all for Ethernet. We move on to SerDes, and SerDes is serializer, deserializer. It's getting more important, more and more important in the automotive, and this is also kind of trend in the automotive for the next years. The number of cameras and displays is increasing in the cars, so we have these central information displays with the car driver information displays. Also, the back mirror displays are occurring in the car, and also the cameras, number of cameras is increasing. So all these parts needs to be connected somehow. And right now there are basically there are several proprietary systems available. So you might know GMSL. There is also APIX and FPD-Link available, and there are kind of no common or open standard compared to Ethernet. But nevertheless, due to the very high data rate here for SerDes, you need to look on the signal integrity here even more, and therefore also the parasitic capacitance needs to be below 1 picofarad here, far below 1 picofarad. We are targeting roughly 0.1, 0.2, 0.3 picofarads here for our devices. So matching is here usually not a problem because the capacitances are very low anyhow. And yeah, such rough conditions as short to battery or jump start are also not considered, and therefore you can have the lowest clamping voltage you can achieve with your device, and this would also mean a very good protection for your PHY. Again, the ESD protection should be placed here close to a connector, as close to a connector as possible, and this is when you recap all the slides we have shown to you, we recommend this in all the automotive applications, or all for all ESD protection applications. And what is also very important for these high-speed devices, very high-speed devices, that you need also to consider your package, and therefore we'll come to this point later on more deeper, and with these package aspects. Right now, Lucas will take care of infotainment and multimedia.
Yeah, thanks, Andreas. So moving on then to the highest speed lines we have. So talking about 10 gigabits per second, or now even higher with USB 4 apart. Yeah, the most common ones are for sure USB and HDMI, and we will not focus so much on the usage of those buses, but again more about their requirements in terms of ESD protection. So again, when we're talking about multiple gigabit bits per second, then again we need a good signal integrity resulting in small parasitic capacitance we add with our ESD protection. So same as for SerDes, we want a capacitance below 1 picofarad. To measure the RF compliance or behavior of the device, Andreas showed the scattering parameters for the Ethernet part, but especially for those multimedia buses, ion diagrams are often used, and we want to show how to distinguish here and decide what is a good ESD protection. So on the eye diagram, we can plot where we sample those signals. So we have an overlay of all those signals of a digital transition with an oscilloscope in persistence mode. And if we layer those transitions of the signal going from 1 to 0 and again from 0 to 1, we get this so-called eye pattern. And on the left-hand side, you see only the PCB tray, so without ESD protection. And we see here that the eye is wide open, and we have the jitter is in a good shape. And on the right-hand side, we see the PCB with ESD device. And now you might wonder, okay, the difference is not that big. And exactly that is what we want to see. We want that the ESD device is adding low parasitics to our line. And you could imagine if we have a bad ESD device, then this eye would be way closer and the jitter would be also more destroyed. So eye diagrams provide a really good indication on our RF compliance of an ESD protection device. So where we're already talking about the RF compliance, there are also some routing considerations we must take into account. And there, as we promised, we prepared a little extra, and this we'll discuss now, and then we move on with our Q&A session. Andreas.
Okay, thank you, Lucas. So as Lucas said, the parasitics, so when you come to high-speed data transfer, the parasitics is a very important topic, and you need to take a very close look on it. And here we have one example where it is necessary. So what you see here is on the left side a graph of clamping voltage over the time. We also shown this graph on Tuesday. You might remind this already. And when we look on the right side, on the schematic, on the block diagram, so our ESD protection is basically containing this ESD functionality, this turn-off behavior itself, but it then also can be characterized by this dynamic resistance we also talked about last time, but it's also having this parasitic inductance here. And also for sure the trace itself to the eye open of your PHY is having all these parasitics, but especially for these high-speed buses, there is this is very important to look also on this very first high peak and to avoid this, and when you think what is the impact, what is impacting this high peak here at the beginning, and this will be here the parasitic inductance of your ESD protection device. And in order to lower this peak, you need to have an ESD protection with the lowest parasitics here, and this will also turn out in the question, what is the best package to choose for my ESD protection. And here we come to another investigation we done here at Nexperia, and what we did here is we compared this SOT23 package and a DFN package in terms of scattering parameters. So again, scattering parameters gives you an indication how much of the signal will be transferred through a system. This is the insertion loss, or reflected from the system. This is the return loss. And also due to the fact that we have a differential signal here, we can look on this mixed mode scattering parameters also. And what is done here on this slide is that we have only the pads of SOT23 and DFN package. So only the pads are here on the PCB, and we see the scattering parameters when we compare them. We did the measurements up to 10 gigahertz just to indicate, or just to show you here to see a real difference. Yeah, you see here small difference at very high frequencies, 4 or 5 gigahertz. And in comparison, there's only a differential line here shown dashed. And what you see here, if you place only the pads, only the footprint, not the device, is that the difference here is not really high. So it's not really important. But then when you put a real device on the PCB and measure it again, and this devices have both the same, so the die on both devices has the same parasitic capacitance of 5.2 picofarads here. But when you measure it, you see here a difference, and very clearly, it can be seen very clearly here in the insertion loss. So there is an improvement of the DFN package by 300 to 400 megahertz. And may ask yourself, what is the reason for this deviation? Because the parasitic capacitance is the same, but the answer is that the package itself. So here for the SOT23 package, we have this leaded pins here, which introduces some kind of stubs in your system for sure, but also they introduces some parasitic inductance here. And also there are some bigger pads where you place your die on inside the package. And all these contributions will lead to a slightly wronger signal integrity here. So as a takeaway, and also to summarize this impacts from the parasitics, you can say that the this leadless package can have some real benefits in high-speed applications when it's not only saving space on your PCB, but it's also giving you better signal integrity performance here, and it's also giving you here and there better ESD protection. Okay, and with this slide, we want to close our second webinar, and we want to thank you for taking the time and to be with us.
For today, I would like to say thank you again for your participation, and I will close the seminar. Stay healthy, and thanks so much for joining from your team Nexperia.
Thank you very much. Bye-bye. Take care.
Thanks. Bye-bye.